Alright everybody, this is going to constitute the first in a series of videos about gas laws. Now some of you may have seen this sort of stuff before, but for those of you that haven't, let's start from the basics. Now whenever you're talking about gases, more so than when you're talking about solids or liquids, there are several characteristics of gases that we want to be able to study if we're going to answer questions about them. One of the first properties of gas is the pressure, usually reported in atmospheres. There is also the volume, usually reported in liters or milliliters. There's also the temperature, that always needs to report it in Kelvin. So if you have a temperature unit that's something other than Kelvin, you have to convert it. And then N, which is the quantity of gas, which is our number of moles. So you got to remember, for the temperature, if you're given a unit of something other than Kelvin, you have to convert it. It's not so much an issue for all the others, although I would recommend getting into the habit of converting pressures into atmosphere is a good idea. And we're going to see when we get to the ideal gas law in the next video that converting volume to liters is also important. Alright? But these two are not necessary for every problem. This is. Alright? So what we're going to talk about are three laws today. These are called Boyle's law, Charles's law, and Avogadro's law. And these will relate, in each case, two of these properties to each other. And that's why they're called the simple gas laws. Simple because they take two properties and relate them to each other. So for example, Boyle's law relates pressure and volume. Alright? Charles's law is volume and temperature, and Avogadro's law is volume and number of moles. But we'll get to those in a minute. What we're going to look at first is Boyle's law, pressure versus volume. So just imagine a container. Let's say it's got a pressure of 1 liter. Alright? And it's full of a bunch of moles of gas. Alright? And let's say, for example, that has a pressure of 1 atmosphere, for example. Now what is going to happen inside that box if we reduce the pressure to 0.5 liters? Well, the important thing that's going to happen is the 6 molecules in there are going to be pushed closer together. So not only are they going to be bumping against each other more often, but they're going to be bumping against the walls more often. And it's bumping against the walls of a container that defines the pressure. So the only thing we can say for sure is that the pressure here is going to be higher than 1 atmosphere. Alright? So as the volume goes down, the pressure goes up, and that's what Boyle's law tells us. Pressure is inversely proportional to volume. Alright? And because if the pressure goes up and the volume goes down, because the amount the pressure goes up is the amount the volume goes down, the product of these two is always the same. So the product of pressure times volume for a gas is always a constant. And that's useful because that allows us to set up a situation where we can compare initial and final values for our volume and our pressure of a gas. So according to Boyle's law, what Boyle's law says is as pressure, or let's say as volume goes up, pressure goes down, or as volume goes down, pressure goes up. The two are inversely related to each other. Alright, so given 3 of the 4 variables here, if these are our initial pressure and volume, and these are our so-called final pressure and volume, we can calculate one variable given the other 3. The only other thing to assume here is, notice temperature and number of moles are not mentioned here, but this equation for Boyle's law assumes constant temperature and constant number of moles. So it's making those two assumptions, alright? And we'll find for each of the 3 simple gas laws there is an assumption like this. But assuming that, let's take a look at an example. says a snorkeler takes a syringe filled with 60 mils of air from the water's surface where the pressure is 1 atmosphere to an unknown depth down below the level of the water. The volume of the air in the syringe at this depth is 7.5 mils. What's the pressure at this depth? Well, notice that the volume of the air in the syringe has gone from 16 to 7.5. So 16 mils above the water to 7.5 below it. So the volume's gone down. Because these are inversely proportional, you should be able to predict that, well, that means the pressure's gone up. But let's just see. We know P1 V1 is P2 V2. What I'm looking for is my P2, so I'm just going to rearrange the equation to get that. So P1 V1 over V2, and so our initial pressure is 1 atmosphere. All right, 1 atm. Our initial volume is 16 mils. Our final volume is 7.5 mils. Notice that we know we're doing things right because we're being asked to find the pressure and our mils cancel out. So what we actually get is a new pressure of 2.13 atm. Exactly what we were expecting, all right? I suppose that really should be 2.1 atm. So as the volume went down, the pressure went up, as you would expect. So that's Boyle's law. P1 V1 is P2 V2. As volume goes down, pressure goes up. They're inversely proportional. Alright, so let's go on to the next one. The next one is Charles's law. Alright, Charles's law actually relates volume and temperature to each other. Alright, if you've ever seen an aerosol can, or, well, obviously everybody's seen an aerosol can. If you read on the side of an aerosol can, it'll say, "Don't heat this up. Please do not expose it to a naked flame." And there is a reason why. If you increase the temperature inside that can, what you're doing is, because the pressure is constant, because there's nowhere for the molecules to go, what's happening is the volume is trying to increase. It's trying to increase and trying to increase and trying to increase because the temperature is going up. Eventually, what's going to happen? Well, if it gets up to a high enough temperature, the volume will try to get big enough that, boom, the whole thing will explode. And that's why you don't want to heat up an aerosol can. Although I'm sure it's a cool thing to do as long as you're not doing it. So they're directly proportional. All right? And so you can say this is true. V over T is a constant because as one goes up, the other goes up. The product of these two is always going to be a constant, just as it was for pressure and volume according to Boyle's law. So Charles's law says as temperature goes up, so does volume. All right? Or as volume goes down, temperature goes down, for example. So we can come up with an equation in the same way as we did for Boyle's law. V1 over T1 equals V2 over T2. All right. Again, with the V1 and T1 being our initial values and V2 and T2 being the final. All right. And this is also assuming two of the variables are kept constant. All right. And what do you think those two variables might be? Well, that's constant pressure and constant number of moles. Out of the four variables, the two that are not involved in the equation are kept constant. So let's look at another problem. The gas in a cylinder with a movable piston has an initial volume of 88.2 mils. So that's our initial volume right there. The gas is heated from 35 to 155 degrees C. From meaning that's the initial, to meaning that's the final. What's the final volume? So we're asked to find V2. Now remember what we said before about temperature. You have to make sure you convert your temperatures into the proper unit, which is Kelvin. So 35 degrees C is 308, let's just say 308 Kelvin. And then 155 degrees C is 428 Kelvin. We always have to do that conversion. So we're solving for V2, all right? And that's going to be V1 over T1 times T2. All right. So what we end up with then is our V1 is 88.2 mils. Our T1 is 308 Kelvin. Our T2 is 428 Kelvin. Now before we calculate the answer, notice our temperature went up. These are directly related to each other, so what should happen to our volume? Well, it should go up as well, and it does. We get a V2, a final volume of 123 mils. It's gone up, as you would expect. Alright, so on to the last law, Avogadro's law. This actually relates volume to the number of moles of gas. Alright? The simple analogy here is imagine blowing up a balloon. Alright? When you blow up that balloon, the more air you put into that balloon, the more molecules of gas you're blowing in there. So the number of moles of gas inside the balloon is increasing when you blow it up. And the volume increases as a result. Alright? So that's a simple analogy to that. The constant variables here would be, what do you think the constant variables are? Well, it's the two not involved in the equation: constant temperature and pressure. Alright? If volume and number of moles are proportional to each other, then V over N is a constant. And so we can say, just as we said for Charles's law, V1 over N1 equals V2 over N2. Alright? And there is our formula. So let's answer the question here. A chemical reaction in a cylinder equipped with a movable piston produces 0.621 moles of gaseous product. Alright? Now notice that says product. 0.621 moles of product. That's kind of important. If the cylinder had an initial volume of 2.18 liters, that means our V1 is 2.18 liters, and contained 0.120 moles of gas before the reaction. Now, before the reaction means before anything happened. That's the initial number of moles of gas. Therefore, 0.621 must be our final number of moles of gas. All right. So what we have to do now is figure out what we're going to do here. Now, as our V and N are directly proportional, as one goes up, the other should go up. So what's happening here? Our number of moles of gas go from 0.12 to 0.621. All right. So our number of moles of gas are increased. So our volume should also increase as well. All right. So V2 is going to be V1 times N1 times N2. So our V1 is 2.18 liters. Our N1 is 0.120 moles, and our N2 is 0.621 moles. Moles cancel. We're left with volume, which we are just going to calculate. So that is, okay, let me try that again. 2.18, that's divided by 0.120 times 0.621 gives us a new volume of 11.3 liters. Alright, so as our number of moles went up, our volume went up as well. So those are the three simple gas laws. And that's it. Thank you.